Hello everyone. Today we'll cover the vibration analysis in turbo machines. In Part D, our focus will be on shaft crack. We cover the different topics in Parts A, B, and C, and we'll continue with Part D today. Okay, now let's look into the cracked shaft. Failing to detect and address the issue may result in progressive expansion of shaft cracks, and ultimately can involve a broken shaft and machine failure. Such an event incurs significant losses and have adverse consequences. As you could imagine, the presence of crack diminishes the stiffness of the shaft. The bending stiffness of the shaft is directly tied to the cross-section area. As cracks propagates along the shaft, the available cross-sectional area progressively diminishes. This causes a continuous decrease in shaft bending stiffness. This reduction in shaft stiffness amplifies its susceptibility to bending under static or dynamic load. This leads to an escalation in first harmonic vibration, 1x, as you could see from the below figure. The greater depths of the crack, the more pronounced the second harmonic, 2x, becomes. This is because crack causes asymmetry in the rotor lateral stiffness. Let's look into the rotor dynamic modeling. Here is the 63 megawatt steam turbine. The circumferential crack was found at first stage bucket. The machines with frequent start and stops are exposed to increased number of passing through the resonance and suffer from extensive heat and cooling shocks. And this can contribute to possible shaft crack. The crack was simulated by a change in rotor diameter at the location of the crack. This adjustment in the model accounts for material portion that does not contribute to stiffness. If you run the model, the rotor dynamic modeling generates rotor response plots as shown below. The first noticeable difference is the increasing in vibration amplitude, indicating that decreasing in effective damping. The second noticeable difference is the decreasing in first bending mode, indicating the decreasing in shaft stiffness. As you could imagine, if the shaft stiffness changes due to crack, the output rotor response will change with same amount of imbalance. The impact hammer test can confirm the decreasing in shaft natural frequency. For your reference, in Part 14 video shows detailed steps on how to perform impact hammer test. As you could imagine, identifying the shaft crack is challenging, because it can obscure by concurrent machine issues such as imbalance, misalignment, or bearing looseness. But if there is an indication of shaft stiffness reduction, you could look into the possibility of shaft crack. Many research papers delve into the topic of cracked shaft and their impact on machine vibration. For a more in-depth exploration, you can find the reference at the bottom. Alright, today we covered the topic related to cracked shaft. In the next video, we will delve into remaining vibration analysis in turbo machines. Thank you for watching, and I'll see you in the next videos.